Hi everyone, I'm Matan. As promised, we're going to talk a bit about type classes. So, let's finish with the embarrassing part first. A few words about myself. Currently I work as a backend engineer at Wix. In the last almost last decade I work in Scala, it's my main tech stack. When I'm not doing that, I'm a father of two lovely daughters, and I always try to convince my wife that I'm the best husband ever, but eventually she will believe me. So after we finish with that, let's start with the outline, what we're going to see. So first we'll explain what is the problem we're about to solve. Second, we'll explain why type classes work in order to solve this problem. We'll see a short live coding and summarize the whole thing. So instead of providing a formal definition, let's start with an example. So our goal is to write a generic JSON encoder of objects. So let's take an example. Given the following class, in this case, is standard point class, having two fields, x and y, both ints, representing coordinates. And we would like to serialize, to encode an instance of point to a JSON string. For example, let's say that for a given instance of point with x equals 3 and y equals 4, the expected JSON string output is this thing in here, field x with value 3 and field y with value 4. Simple. So the next solution is actually quite straightforward. We can extend the class point with the new behavior. Let's call it a code. And in this case, the solution is very, very, very simple. Let's try a more advanced example. So here we have the class point with the new behavior we are already familiar with. And in here we have a new class item that has three fields, ID and description, both strings, and a new field, price, which is an int. So in this case, the solution is also simple. This is the encode behavior. Every field has its own corresponding value. Cool. Another example is to take the delivery class, which has two fields, which are complex types, item and point, target. And this case is also very solvable. We can call the already defined encoding behavior of each type. Cool. This is a usage example. Let's say that we have this kind of delivery instance with an item and point. We call the encode, and this is the expected JSON output string. Easy. However, what can we do in this case? Let's say that we have an urgency class, and we have a courier which has a field of list of deliveries, and a field of urgency which is optional. In this case, the implementation is not straightforward, because we cannot extend the list and the option classes, because they are final classes. We cannot do this anymore. So we can apply a wrapper class, but it doesn't work, not easily. And we would like to keep the previous logic and to make the implementation as simple as possible. So if we list the problems that we've seen so far, the solution, the extended within behavior solution cannot be applied if we are not on the source code. If the source code is not accessible, we cannot extend the class. Second, in each case, we had to manually JSON encode all primitive types. For example, the string type, we had to manually JSON encode by wrapping it with double quotes. Int fields, we had to manually remember to print them as it is, without quotes. I would like to write the encoder once for each primitive types and to use it everywhere. In addition, complex hierarchies lead to complicated implementation. So, let's try to solve all the above. So, this is the first iteration of the solution. Like 80% of the engineering problems, let's do some kind of one level of indirection. We extract the encoding behavior to its own place, to its own generic trait. And in this case, we see that every class that implements the JSON encoder of a generic type T defines a new behavior encode which accepts a new instance of type T and responsible to return the JSON string. Okay. In these lines, 5 to 7, we see a concrete implementation of this new trait. In this case, we implement point encoder, which creates a new JSON encoder of type point. And in here, we just copied the point encoding behavior to the encode implementation. Easy. In this line, there is a utility function that invokes the encoding behavior. It receives two arguments, one the type T, and the other one an instance of the encoder of type T. And it invokes the encoder on the given type, given instance. And in here we can see a usage example. We call the print JSON, we provide it with the current point, with the point encoder, and it works as expected. However, it became some kind of a dirty API, a very awkward API. And why is that? Because I don't want to explicitly provide the point encoder for each type. I would like it to behave as natural as possible. I would like to provide the print JSON the current instance of point, and that's it. So, how can we do it? Luckily, we work in Scala, and there is the implicit mechanism. And a short reminder for someone who's not familiar with it. Let's say that there is a function call that expects an implicit argument of type T, and what does it mean? The compiler tried to find an implicit value of type T in scope, in current scope, and if such value exists, then the compiler assigns it to the function call by itself. Let's see an example. Here we have a function called prebalance. It has two argument lists, one with a coins argument, which is an int, and the other one is currency argument, which is implicit currency argument, which is a string. In addition, there is an implicit string in scope with the shekel symbol, and in this line in here, we see an example of invocation. Here, we invoke the function with the explicit argument only, and the compiler knows that there is a string in scope, implicit string in scope, and doing the assignment by itself. Of course, we can call this function, the same function, with an explicit argument. It works as well. So, let's try to improve the previous solution. In this case, the JSON encoder trait remains the same. And we just said that the point encoder is now an implicit value. So, in this case, we changed the signature of print JSON to have an implicit encoder instead of an explicit encoder. And now, the function call became more natural. And in this very moment, we just implemented our first type class. So, if we revisit the problem definition, first part is done. So, now for a more formal part, this is the type class definition from Wikipedia. In computer science, a type class is a type system construct that supports ad hoc polymorphism, and it really scares me. So let's see some kind of more TLDR version of this definition. A type class is a group of types that share a known set of behaviors. And actually, the class in the type class term actually refers to a group, to the group of types. So, actually, for example, all types, all group of instances that share a common behavior of generating unique identifier, or other type classes we're already familiar with, all classes that belong to the same group that enable encoding the instance to a JSON string. Cool. So after the what, let's focus on the why. Why should we use type classes? So first, single responsibility. Instead of let's take the point class, for example. Instead of the class to be responsible for storing the data of both coordinates and other point related behaviors such as translation or adding or something like that, the point class should not be responsible for how to encode itself to JSON. So it makes more sense to extract this behavior to its own dedicated place. Second, it enables us to add new behaviors to existing types, even if we don't have an access to the source code. For example, final classes. Now we are able to extend list and option and string and all of the sealed classes. Another thing is it enables us to have ad hoc polymorphism. We can combine new behaviors very, very, very easily. And one of the key features is that we fail fast. If there is an error, the error is on compile time, not on runtime. For example, if you try to encode some kind of class that there is no such encoder in the scope, then the compiler says, I don't know what do you mean. This is the compiler. And if someone is familiar with the default Java object serializer, then you know that the failures happen on runtime. And this is not fun. Okay. So, let's continue. So, this is our previous solution so far. And it is not perfect yet, because as I said, we have to manually encode primitive types. In this example, we manually encode the int type of, in this case, the x field and the y field. And in item class, we also have to repeat this behavior. So I would like to have a better code reuse. Okay, so now we understand that in order to support encoding ints, we have to define a new type class. JSON encoder of ints. And this is it. This is an implicit int encoder. And in this case, encoding ints is very straightforward, just to provide the string value of the int. Now, in order to define a point encoder, point JSON encoder, we have to do two things. First one is to have a dependency on an existing JSON encoder of int in scope. Then, the second thing is to use it, to reuse it. In this case, we see that in order to encode the int value of x field, we have to call the encoder encode function on the x field, same thing on y. Let's revisit the item class. In this case, in order to properly decode item to JSON string, we have to decode ints and strings. So we already know how to JSON encode int type. Then we have to implement a string encoder. In this case, we just take the given string instance and wrap it with double quotes. That's it. And here, we just have to, again, create new dependency of string encoder and int encoder, and we can use them as simple as that. So, right now, actually we solved the code reuse issue. And now, in order to encode complex hierarchies, the implementation became much simpler because we just use the encoders already in scope. However, we created a new problem. I don't want to use the type class, to reference the type class by its name, because it's not the main business in the function. Actually, I don't care what is the name of the reference. I would like to use it either as it is, anonymously, or I would like to make the API calls to look more natural, like if they were part of the object itself. So, before solving that, let's have a moment on this. This is a great thing that we already achieved. We added a new behavior to a string despite that it is a finite class. We extended it with a new behavior like inheritance. I've already talked about the alternative solution that we could create a wrapper class to string that proxy all calls to the underlying instance, and the wrapper class should implement the JSON encoder. However, if we do this, then all the usages in the application should refer to the wrapper string instance instead of standard string, and then the code becomes very, very unreadable, and this is very not practical solution. So, right now, what we would like to solve is to make the API calls look more natural. So, in this in the slides, I will show one solution to how to make the API calls look as if they belong to the object, and in the short demo, I'll show the other solution. Okay, so our goal is to make the API calls to look as natural as possible as part of the object. In other words, to avoid these kind of calls, to encoder.encode. So, in order to do so, let's define an extension method, an invocation helper. In this case, we define an implicit class, call it JSON encoder syntax, and it defines a new function called to JSON. I call this function in a different name in purpose in order to us to be able to distinguish. And the extension method just invokes, call the invocation, call the encode method of the encoder on the given type T. And by doing this, it makes the solution much cleaner. Let's focus on the lines. And we can see that now instead of calling the int_encoder.encode on the field X and Y, we can call the toJSON directly. And in this case, it looks like, it calls the encoder code, but it looks like the toJSON is really part of int type, same as string. And it makes a much nicer API. So, in this point, we can say that the problem is solved. Okay, so few more things. Compile time safety. As I said, we cannot call the encode behavior on a type that does not have a meaning of encode, which means that we don't have an implementation of how to encode it to a JSON string. And by talking more technicality, it means that there is no instance of JSON encoder in scope, and then the compiler throws an error. And in the demo, I'll show how can we tweak this error to make it more user-friendly. However, type classes are not perfect. And why is that? Because the solution is based on traits with generic types. And it means that we have to know the exact concrete type of the type class implementation. It doesn't work well if we work on the super type. And let's see an example. This is a textbook example. Let's say that we have a trait showable, a generic trait showable, which defines a new behavior of show given an instance of type T, it returns a string representation of the T. This is another textbook example. We have a trait shape and two concrete implementations of shape, string, circle and rectangle. In this case, we define new showable concrete implementations, how to show a circle and how to show a rectangle. In this case, we define also a showable list, how to show list contents, and again, it has a dependency on a generic showable, but it fails in here. This is our invocation method that given some kind of type T and given a showable of type T, it invokes the showable on the type T. We have a list of shapes. The type of shape is list of shape. However, calling this line fails. And why is that? Because the compiler said, I don't know. I couldn't find an implicit encoder, an implicit type class implementation for showable list of shape. I have showable of list of circles, showable list of rectangles, but I don't have any shape concrete implementation. Okay, so in order to wrap things up, in order to work with type class, we have to do three things. First one, to create a generic trait that defines a new behavior. In our case, it was the JSON encoder for a generic type T. The second thing is to create a concrete implicit instance of the type class with an implementation. In our case, it was, let's take the concrete type point. We define the point encoder as we've seen. And the third step is to have a much nicer API. We would like to call the encoding behavior directly instead of invoking it from the type class itself, from the JSON encoder. And then we define the extension method. Okay, now we'll have a short demo. Okay, so now this code also was also shared from the previous link. In here we have a very, very small project that define all classes that we see in the slides, and also the JSON encoder type class that was defined in the slides as well. This is the extension method that we're already familiar with it. And there is also the concrete type encoders, but in here we have a different syntax. In the slides we've seen how to use the extension method to make the API call as the function call to make it as it was an integral part of the type. In here there is a different way. I use the implicitly keyword in Scala, which means instead of defining an implicit argument of this function, then I summon the type class concrete implementation of JSON encoder. And if I have this anonymous reference, then I can call the encode method on the field X and continue with the flow. Same for Y. If I would like to encode item, then I summon here the JSON encoder on string type, and so on and so on. Okay, so in here, and then I wrote this hint that if there is no encoder, try importing this class. By the way, the implicit execution context of Scala works with the same implicit annotation. Okay, and final thing, there is also type class derivation, which means that usually you don't have to write the type class by yourself. There are lots of libraries, Cereset, spray JSON in this case, that you can provide a small hint and the type class code is generated by the compiler, which is nice. In this case, I defined the JSON support, coding support for all the three types, point, item, and delivery. But in this case, this is the only code that I had to actually manually write by myself. As you can see, point format, this is the spray convention. It means that I use the function JSON format to accept the type point, and that's it. And then the compiler understands that in order to provide support for spray JSON, it has to have int JSON format, which is already defined in spray, which is very, very nice. Okay. So, this is the last slide. To sum things up, type classes are interfaces that define new behaviors. Type classes enable us to add new behaviors to extend existing types without having an access to the source code. As we already seen, finite classes were able to be extended with the new behavior. Type classes provided with added polymorphism, and usually they are expressed with generic traits and implicit calls to make a clean API. And by leveraging the compiler, it enables us to write less code because the compiler writes code instead of the developer, as we've seen in the implicit calls and in spray example. And of course, there is a type class derivation that enhances the following point. That's it. Questions? Yes?
There is a syntactic sugar for the implicit argument, where you can, I think it's called...
Context bound?
Yeah, context bound.
I'll repeat the question. Yes.
Yeah.
Okay, so there was a very, very nice comment from the crowd. There is an implicit, there is a nice syntax called context bound. I started to implement it in the demo, but I wanted things to be able to fail because the hint wouldn't work without it. So it means that instead of getting a generic type T, we can set a bound on the context of the generic type T. It says that it's not just an arbitrary T, it is a T that should implement a JSON encoder. And it is much safer.
I think there is another feature where if you inherit from the trait of JSON encoder an object and you put all the implicit definitions there and you import only the trait, it automatically imports all the implicit of the inheriting object. I think it's another thing that usually people do.
I'm not sure, but I will be happy to see that afterwards. I think that the imports are taken from the object itself. I think, but
Yeah,
let's work on it together.
for it.
Let's see it together. Cool. Another question? Yes.
It's a list of shapes.
Hi, we work together.
Couldn't the list of shape thing be solved with variance?
Could you please repeat that?
We had a circle and shapes stuff, and there was the error on list of shape, but isn't it solved with the variance?
Provides?
Variance.
Variance. I'm not sure. The question was if the just a second. Okay. The question was if variance is able to solve the shape example. I'm not sure, because if you are using variance, then you say that this generic type is bounded to some constraints. You don't have a concrete implementation, a concrete type. And then the compiler is not able to find the concrete implementation of the JSON encoder in our case. So I don't think it will work. Other question? Yes, please.
I have a question. When you implemented the encoders yourself, you had to name the keys, the JSON keys. X. Yes. When you implemented the encoders, for example, for point, you had to name the keys X, and then point.x, and Y, point.y. Could you use some sort of reflection, something to get
Of course. Okay, so it's a great question. The question was, in the example of encoding a point to a JSON string, I have to explicitly decode the field name X and then to use the int encoder of the value. So the question was, is it possible to automate this whole process? And the answer is absolutely yes. I wanted to make it as simple as possible, but if you can use reflection or shape, reflection no, Magnolia, Shapeless, all the other great libraries, then you can have, in a safe way, the field name and, of course, the encoded value that you already seen how to do it. Yes. Other questions? Okay. Thank you very much.